Hello, welcome back to another math video today. And we're asked to evaluate this crazy integral over here from 0 to 2019 of 1 over ceiling function of x squared plus ceiling function of x dx. So how in the world would we even tackle this? This looks crazy. In fact, we may not have even done a ceiling function before inside an integral, so how does it even expect us to do it, and it's even squared? This looks crazy, and it's even in the denominator. How in the world would we do this? Well, first, let's refer back to the definition of a ceiling function. So ceiling function of x, that's how it's referred to as, is just the least integer greater than or equal to x. So what does that mean? That means if x is a decimal, we just round up to the nearest integer. For example, ceiling function of negative 0.5 is just 0. And if it's already an integer, it just remains the same. So ceiling function of 1 is just 1. So that's, hopefully, you get an intuition of why it's called ceiling function, because it takes the ceiling of something. Like you go up to the nearest integer, just like the ceiling is above you, that kind of logic. So now that we know the definition of these set of brackets over here, how in the world would we apply it so that we could solve this integral? So what we do is we can simplify this problem by interpreting this integral as asking us the area under this curve from 0 to 2019. Because that's what integrals do. When you integrate from two different x values, it's asking you the area under the curve, or the net area, depending on whether it crosses the x-axis. So let's graph this and see how we can find the area under this curve formed by this expression. So to graph it, first let's graph 1 over x squared plus x without the ceiling function. And to graph this, we see that as x goes to infinity, then our expression just goes to 0. So it has horizontal asymptote y equals 0. And we can see it goes down. Also, we only care about x is greater than or equal to 0 because our integral only goes from positive values of x from 0 to 2019. So now that we have that down, let's try to see if we can graph this expression inside the integral with the ceiling function. Well, to do that, we must first note that ceiling function of x only changes values whenever we cross an integer. Other than that, it just stays the same. For example, ceiling function of 0.3 just rounds up to 1, while ceiling function of 0.6 also just rounds up to 1. It isn't until we get past 1 that it starts rounding up to 2. And that's the kind of logic we want to see in order for us to evaluate the area under the curve formed by this expression. So to graph this, we just have to take any value between two integers to find the value for this expression for all x between those two integers. For example, between x equals 0 and x equals 1, ceiling function of x always rounds the number up to 1. So our expression is just 1/2. So that means between x equals 0 and x equals 1, our expression is always equal to 1/2, constant value of 1/2. As you see that bar on top of the box over here, that's the top of the box. Similarly, between x equals 1 and x equals 2, we can find that our expression is just the constant value 1/6. So between x equals 1 and x equals 2, it's just 1/6 and it stays 1/6 only. And it isn't only until we cross 2 that our expression goes up once more. And we can also see a pattern. We might think that this area converges under this curve formed by this expression because the box keeps getting smaller and smaller and smaller, and the area might actually be finite, and then this expression would actually have a value rather than it just being divergent. All right, so how would we even find the area? That's a different question. So the area for a rectangle is just width times height, and the width here is just 1 because the difference between two consecutive integers is just 1. From 0 to 1 is just 1. 1 to 2 is just 1. 2 to 3 is just 1. Now the height is something different. The height here is 1/2. Height here, 1/6, etc., etc. So the height from integers, we can generalize. The height from integers k minus 1 to k is just equal to 1 over k times k plus 1. And you can verify this use your intuition, logically. Just verify this. Make sure you understand where this is coming from before we proceed. All right, so now we just want to sum up the areas for all of these boxes until x goes all the way to 2019. And that will be the value of our integral. So our integral is just equal to the sum from k is equal to 1 to 2019 of 1 over k times k plus 1. Make sure you understand where this is coming from. 1 over k times k plus 1. You can see this works because when k is equal to 1, this expression gives 1/2. And 1/2 is just the area of this first box. When k is equal to 2, this expression gives 1/6. And 1/6 is the area of the second box. So on and so forth. And we go all the way to 2019 because that's our limit of integration. All right, so now that we have that down, we just need to identify what kind of series this is. And it turns out this is something called a telescoping series. Telescoping series is just exactly this right over here. 1 over k times k plus 1. So to find the sum of a telescoping series, we employ a method called partial fraction decomposition. So what that is we try to express 1 over k times k plus 1 as two separate fractions. And we don't know the numerators of these two fractions yet, but we can figure them out in a moment. So let's just say this is equal to a over k plus b over k plus 1. The reason we have denominators k and k plus 1 is because they're the factors of the denominators on the left-hand side over here. Whenever we want to decompose a fraction, we always split it up by the factors in the denominator. All right, so how will we solve for a and b? Well, we just multiply through by k times k plus 1 to get 1 is equal to ak plus bk plus a. And regrouping, we get 1 is equal to a plus bk plus a. Now we can use a method called matching coefficients to figure out a and b. The reason we can do this is because this equation holds for all values of k, no matter what k is. So on this side, no matter what k is, there is no k term. And that means the coefficient for the k term on this side is just 0. And the coefficient for the k term on this side is a plus b. So matching coefficients, we get a plus b, the coefficient for k on this side, is equal to 0, which is the coefficient for k on this side, because there is no k term. Similarly, for the constant term, we match coefficients once more, and we get a is equal to 1, much simpler than this. And then we can plug in a equals 1 to find b is equal to -1, and plug back in here, because a equals 1, b equals -1, that means 1 over k times k plus 1 is just 1 over k minus 1 over k plus 1. And we get a minus sign here instead, because b is equal to -1. So I have that written here on the other side. And now we can rewrite this expression right over here. And sorry, this should be to 2019. I don't know why it says 2018. But from k is equal to 1 to 2019 of 1 over k times k plus 1. Remember, this is just the same thing as 1 over k minus 1 over k plus 1. So we can plug in values of k into here instead of here to evaluate our sum. Doing that, for k equals 1, we get 1 over 1 minus 1 over 2. We get that here. Plus, plugging in k equals 2, 1/2 minus a third. Plus, and then we keep adding. A third minus a fourth, plus a fourth minus a fifth minus a sixth, etc., etc. Keep adding until we get here, all the way to the end. and we find something miraculous happens. We see a whole bunch of terms cancel. Negative 1/2 and 1/2 cancels, negative 1/3, and we get a positive 1/3 next here. That cancels as well. And all of them cancel. The 1 over 2018 and negative 1 over 2018 before that cancels. The negative 1 over 2019 and 1 over 2019 cancels. And the only two terms left is just 1 over 1 and negative 1 over 2020. So we get this expression is just equal to 1 minus 1 over 2020, which is just equal to, and I have no idea why it says 2020 over 2019. I apologize. Let me fix that. 2019 over 2020. Sorry, this is incorrect. And this is our final answer. And remember, our sum here is just equal to our original integral right over here. And in the end, we get our integral from 0 to 2019 of 1 over ceiling function of x squared plus ceiling function of x dx is just 2019 over 2020. Crazy. So it actually did simplify crazily over here when all these terms canceled in the end. Now that's amazing. But this gives us more insight as to how we should evaluate integrals with ceiling functions or even floor functions, because floor functions are just the opposite. They round x down instead of x up. So sometimes when we use this method of finding the area under the curves for ceiling functions and floor functions, we might not get a telescoping series. Sometimes I've gotten geometric series, gotten all types of series before that we've needed to evaluate in order to evaluate integrals with ceiling functions and floor functions. But in general, whenever you see a ceiling or floor function inside an integral, you want to think of the areas under each one of these boxes and think geometric series, telescoping series. What kind of series are you dealing with to find the areas of all of these boxes combined? And in this case, we got our final answer to be 2019 over 2020. So I hope you enjoyed today's video. Please comment down if you have any feedback or anything you'd want to add to help other people out. Also, if you want to contribute in any other way, your own solution or some other creative method of attempting this problem, please comment down below too. If you liked the video, please give it a like. And thank you. Bye-bye.